divided by 0.785 is equal to 3822. 3,822 feet per minute. Okay, and the velocity coming out of that turn, out of that elbow, is going to be the same thing. Okay, now what's the velocity pressure? Same formula we used before, right? It's going to be equal to the velocity divided by the square, the velocity divided by 4,005. Let me get this back here. Okay, velocity pressure is going to be equal to the velocity over 4,005 squared. The velocity we just calculated was 3822 over 4,005. And we're going to square that. And it's going to be equal to okay, I'm going to square that. And it's going to be equal to, did it square? Okay, good. Point, you know, it goes so fast on my screen, I didn't notice. I was looking away. 0.91. Okay, so 0.91 is the velocity pressure. Okay, velocity doesn't change, so the velocity pressure doesn't change. And what is that? What are the units on that again? Always the same, inches of water. Okay, as we move forward, like once we get past the midterm, there might be a question too on the midterm, maybe, but for the most part, I'm going to try and make sure that they're changed all to the American, English or American units. We will work with, at some point, we're going to work with international units as well. So 0.91 inches of water. Okay, so now we're going to calculate the static pressure loss that we have here. So how are we going to calculate the static pressure loss? Anybody got any ideas where we might go to find out how much loss we have at an elbow? What do we got in the book? We have charts, right? In this case, we're looking at chart 7. Let's take a look at chart 7. Yeah, oops. Wrong. Chart 13. Yeah, you're right. Chart 7 is the velocity. We have a chart in there where you don't have to do the calculations. You can just go to the chart, change velocity. You can also do that on chart 5A. Remember the nomograph? You could actually do a lot of these calculations on chart A. 13 was it? Elbow losses. Okay, so what factors determine how much losses we have at an elbow? Well, there's basically two of them. One is the ratio of the radius of the turn to the diameter of the duct, right? The larger the radius of the turn, the more gradual the radius of the turn, the lower the loss that you're going to have. The smoothness of the transition is also going to affect that. And the reason why these transitions may not be very smooth is because you can go anywhere from like a sudden right turn, which is like a mitered, like a picture frame, right, to multiple piece transitions, 3, 4, 5 piece transitions, where the more pieces there are, the more gradual the turn, the more smooth the turn is. To, if you have PVC ductwork, you might have a completely smooth transition. So in this case, we have, I think the radius of the diameter was 2. I think they told us, right? And how many pieces was this particular elbow? Okay. Oh, it's a smooth transition, it looks like, right? Okay, radius of turns, and it looks like a smooth transition. I don't see any sections in it, and so on and so forth. So for a smooth transition, radius of 2, what's K equal to? What's our loss factor? 0.13, right? And so what is our loss of pressure as we go through this transition, this elbow? It's going to be equal to the velocity pressure times K, right? There's also there's also sometimes a density correction factor that might be on the end of that, right? We're using 1 because we're working most of the time at standard temperature and pressure. But again, if we were in Denver, a mile off the ground, we would put, I think the correction factor might be something like 0.83 or something like that. Okay, but we're not worrying about that. So K is 0.13 times the velocity pressure, which was 0.91. So what is our loss due to the elbow? What does that equal to? 0.13 times 0.91? Okay, I get like I'm going to call it 0.12. Okay, so where our loss is 0.12 inches of water. Okay, so let's see what we have here. The static pressure was minus 2 inches. The static pressure now is going to be minus 2 inches less the 0.12. I'm actually going to add the 0.12 because we're losing static pressure, right? So it's actually going to be 0.12 negative 2.0, right? And we're going to lose 0.2 of an inch of static pressure. So I'm going to add that 0.12. And now our new static pressure is going to be 1. Actually, I'm not going to do it that way. I'm gonna minus 0.12. The new static pressure has to be 2.12. Okay. Why did I add that instead of subtracting it? And this is going to clarify a little bit of confusion that we had on the contraction also. The static pressure here has to be higher, a bigger negative number than the static pressure here, because you're really losing static pressure through this transition. So this can't be lower here than here, because if it was, the air would be going the other direction. That makes sense? Right? The static pressure is how much suction there is. So the static pressure here can't be 2.1 and this be 2, because the air would be going the opposite direction of the arrow, wouldn't it? So this has to be a lower static pressure. So even though we're describing this as a loss, the loss loss of static pressure is taking place as it moves through this transition. So if this static pressure is 2 inches, this static pressure must have been a bigger negative number. And the loss is the difference between the two of them. Okay, look at me and make a face like you understand what I'm saying. Right? That makes sense, doesn't it? Okay, it can't be the other way. So intuitively, you know that the static pressure has to be a bigger negative number at 2 than it is at 1. That's why we were having trouble with the contractions, because we lost sight of that. That it's a bigger negative number. Remember, we were looking at the contraction before, and this came out to be 2.8 because we kept adding static pressures. In other words, we added the loss we subtracted the loss to make it a bigger number at 2, because it has to be a bigger number at 2. Has to be a bigger number at 2 than at 1, because otherwise it would go the other direction. Yeah. Yes. I'm sorry. Say again. You want to know something? I'm gonna write this. It's the same equation, right? The velocity pressure, like for the contractions. For the contractions, we were using contraction and expansion. We were using the static pressure coming out is equal to the static pressure going in plus the change in velocity pressure minus the K times the change in the velocity pressure. One of those, a change in velocity pressure, represents how much faster the air is moving, the conversion from static pressure to velocity pressure. It's not a loss. It's just a change of energy, right? The K times the change in velocity pressure represents how much energy you've lost going through that transition. I'm going to give you a version of this for contractions going one way with positive and negative numbers on the equation, rather than just the one equation they give you in the book, and a separate equation for when you're going through an expansion, right? But the idea here is when we're going through here and it's going into a contraction, right? Where static pressure is going to be equal to the static pressure here is going to be equal to this. This is going to be equal to the static pressure at 1 plus the change in the velocity pressure. Well, this is moving faster. The velocity pressure is going up, right? The velocity pressure is going up. It makes the static pressure a smaller number, a negative number. So we're actually going to subtract that change in velocity pressure from this static pressure. It's going to be a negative number. And then in addition to that, we have to deal with the loss, right? Well, we know we have to have more of a suction than just what's converted. In other words, this was 2 inches plus 0.7 inches, right? Minus 2 inches and a minus 0.7 inches to get negative 2.7 inches because it's moving faster here, right? So it's got to be a bigger negative number because the total pressure has got to be equal. So this is a bigger negative number. In addition to that, we're going to lose energy. So this suction has to be even greater than that. It's got to be, we've got to subtract the K times the velocity pressure from that to get an even bigger negative number to make up for the loss of suction pressure between 1 and 2, right? So this is going to be negative 2, negative to 0.7, and negative to 0.1 for the loss. Because each one of those things that we're subtracting from that negative 0.2, right, or negative numbers that we're adding, you can look at it either one. Each one of them is making up for what we're losing as we do this conversion in static pressure. What we need here in order to achieve the 2 inches here. It's kind of working backwards, isn't it? In other words, we're figuring out what static pressure we need here to get the 2 inches that we want here. And that's really kind of the way you almost always work, because you're starting at the hood end and you need 1 inch of static pressure at the hood end in order to get the capture velocity you want. So in order to get that 50 feet up the ductwork, you need 2 inches to make up for the static pressure you lose in the ductwork. And in order to keep that, you need 3 inches after you get to the elbow. We're going to get to that at the end. That's all going to come together at the end as we go through this. Okay, so at any rate, this is what we found, and we filled in all these numbers, and I think we're set on that. Okay, that's a negative, right? It's a negative 2.12. Okay, so let's go on. Now, hood selection, I'm going to go past that for a second. And I'm going to go up to duct friction losses. Got the same deal here, right? So what happens here? 12-inch diameter. What was the area for 12-inch diameter duct? It was 0.785. So the area is equal to 0.785, 12 inches in diameter. The diameter doesn't change. That stays the same, 0.785. What about the volume of air going in, volume of air coming out? It's the same. Not going to change. What about the velocity going in, the velocity coming out? That's going to stay the same also. Let's calculate it. 12-inch duct, 1,000 CFM. Okay. Okay, so the velocity is equal to Q over A is equal to 1,000 over 0.785. All these are in feet and so on, feet and minutes, equals 1,000 divided by 0.785. My phone just went off. Let me just check, make sure it isn't these guys that are on. Okay, what do you guys get? 1274? Okay, 1274. What's the units? Velocity? Feet per minute. Okay, good. Okay, so velocity is 1274. Feet per minute, 1274, same velocity, because we didn't change the diameter. Okay, so what's the velocity pressure? Are we doing anything different really here than we've done before? Right, the velocity pressure is going to be equal to the velocity over 4,005, because we're keeping the units the same. Simplifies it when we keep the units the same. 1274 over 4005 squared is equal to 1275 divided by 4005. Did I make a mistake? I did? Okay, clear. 1274 divided by 4005. Okay, I'm going to square that. And it's 0.032. 0.0, is that right? Nope, I did something wrong there, right? Somebody's definitely trying to get in touch with me. 1274. Yeah, I know, I'm going to have to go over there and get it. Divided by 4005 equals 0.3. Okay, so let's square that. Should be like 0.09, 0.1. Okay, say 0.1 inches. Okay, is equal to 0.1 inches of water. Okay, that's our velocity pressure. 0.1. Okay, now velocity pressure coming out of that 20 feet of duct is going to be the same, right? Velocity is the same, the velocity pressure is going to be the same. 0.1. Okay, now the length of this is 100 feet. Now we want to figure out what the loss is here. So now what determines the losses in ductwork? Well, most of the time we're going to be using, to figure out what our loss is, right? We're going to be looking at K, a factor for ductwork in this case, right? We're always going to have some factor that we're going to use to determine what the rate of loss is. K times the velocity, right? Velocity pressure rather, right? So now there's another, besides K, there's another factor. It's called R for roughness. So we're going to look up K first. And K, I think, is going to be, what chart is K on? Let's see, galvanized, let's see, ductwork. What chart is that? We can get that from chart 5. We can also get it from is chart 7? Or is that the velocity pressure again? Chart 7 is the velocity pressure. I'm going to go to chart 5. Chart 5 is a good fallback chart because if you like using nomographs, you can save a lot of trouble with that. It's kind of like having a slide rule or something like that to do this with. Chart 5, here we go. Here's chart 5. Now, what's this going to do for us? Duct friction losses, right? Here's the duct friction losses. This is a standard K value for all duct. You apply this for any duct that you have. This is what you would use your friction loss. But it doesn't make any sense, right? Why would we have the same friction loss for galvanized steel ductwork versus plastic versus, like a concrete duct, which may be very rough, which I guess, can turn up maybe, right? If it goes through a floor or something like that. Why would this? We need something besides this, and that's where that R factor comes in. That R factor is the roughness. This table, this duct friction loss, is intended for galvanized iron round duct. Okay, you use a correction factor R for all other duct. For galvanized duct, R is equal to 1, so you can ignore it. So let's take a look at what the friction loss is going to be. We're talking about. We're talking about, let's see. What's the duct diameter again? How much? 12 inches? 12 inches is the duct diameter. Here's the duct diameter right here. And what was the flow rate? Q, 1,000, right? So I'm going to go up here. I can actually draw a line with this. Annotate, draw a line. So I'm going to draw a line between 12-inch diameter and 1,000 flow rate. And what do you get for the K for the friction loss due to ductwork? K is equal to, well, this is 0.02, this is 0.015, so it's 0.016, 0.017, 1.8, 0.019, it looks like. You guys happy with that? Is that okay? Look happier. right? 0.019. We all agree, right? Okay, so 0.019 is what our K factor is going to be. So our static pressure loss, the amount of static pressure that we're going to lose going through this transition is going through this how many feet? 100 feet of ductwork is going to be equal to 0.019 times the velocity pressure, which was equal to zero point 0.1, times the roughness factor, which is 1, times, I left one more thing out of that. The one I got, times the length of the ductwork, right? It's going to be different. Right? This is per foot of ductwork. So it's going to be the length of the ductwork, which is 100. So this comes out to 0.019 times 0.1 times 100 equals 0.19. So we're going to lose 0.19 inches of water suction going through that transition, right? Going through that 50 feet of ductwork. So if I go back here, right? If I go back here and I say to myself, well, the static pressure started at 2 inches, and coming out of this run of ductwork, I'm going to lose 0.19 inches of water, of suction, right? Well, that means that at number 2, it has to be that much higher, right? So that has to be a static pressure of negative 2.19 in order for number 1 to be a static pressure of negative 2.0. Make sense? I see uncertainty. Sure. Okay. Okay, let me get a fresh piece of paper here. New. I mean, just looking at the formulas can get a little confusing on this. I have a long length of ductwork, right? The static pressure here, I'm going to measure the static pressure right there, is negative 2 inches of water, right? The static pressure here, air's going in this direction, I'm going to lose energy. I'm going to lose, the velocity pressure stays the same because the velocity is not changing, right? So the total pressure is equal to the velocity pressure plus the static pressure, right? So what's going to happen is as I go through here, I'm going to lose energy here. This total pressure is going to go down, right? So I'm going to lose energy as I go through here. So what's going to happen is that at this end here, the static pressure is going to be different than it is here, right? It's really this end is driving the process. We're doing it backwards, but this end is really driving the process. In order for the static pressure to be here, to be negative 2 inches, I have to have a static pressure here that's equal to that negative 2 inches plus the amount of loss that we're going to have going from here to here, right? So that loss we know is going to be 0.19, right? That's how much energy we're going to lose going through here. So this has to be 2.19 in order for this to be negative 2. Make sense? Okay. Not only that, look at it this way. If I added this instead and it became out 1.81, which direction's the air flowing? The air is always going to go to the place where the suction is bigger, right? It's not, when you have a vacuum cleaner, the air's not going to go out, it's going to go in, right? So it's always going to go from the area where the pressure is higher to where the pressure is lower, right? So if I subtracted this, and the suction pressure here were 1.81, I made a mistake and subtracted it. The only way that this would work is if the air is going this direction. It's going towards the lower pressure area, towards where the suction is stronger, right? That's not what's happening here. It's going this direction. So this is negative 2.91 inches in order to make up for the frictional losses. In a perfect world, there would be no frictional losses. This would be the velocity pressure would stay the same, And the static pressure would stay the same. It'd be -2 inches here and -2 inches here. But since there's losses, this static pressure has to be a bigger negative number in order for the air to move in this direction and make up for those static pressure losses. Make sense? Okay. It'll come to you. If it seems a little odd now, it'll come to you as we work through these. Okay, let's take the next one. Branch entry losses. Okay, so this is really the same deal. The only funny thing about this is, what do you think is going to determine what the that K loss factor is going to be for a branch entry? Okay, this is going to be kind of a transition, but all of the losses are going to be assumed to be in the branch, right? So this is where the losses are. This air is going to pretty much going to keep move straight through here. It really doesn't change velocity because this big duct and these two little ducts are sized so the same amount of air, so that when they combine, right, there's no change in velocity. This takes the quantity of air that you need to combine both of these and keep the same velocity at same coming out, assuming that you design it correctly. Okay, so you size the ducting correctly. So we're going to take most of the losses in that branch. Okay, so now it's going to come in here. What do you think is going to determine what that K number is, whether that's a big K number or a little K number? In other words, what makes for more turbulence? What makes for less turbulence? Well, if I go in and a T straight in at a 90-degree angle, that's the worst case because that's an enormous amount of turbulence. The air's got to completely change direction. But if I go in at a very flat angle, it's much less energy loss there because the air can it's kind of like cars. Imagine cars merging into a highway, right? Same kind of deal, right? So this angle determines what that K factor is. And the velocity in this branch is what determines, and that K value determines how much loss you have in here of static pressure. Okay, so let's take a look at it. Velocity of entry, the velocity in this duct as the branch is approaching it is equal to 4,500 feet per minute. The branch entry angle is 30 degrees. We need a table to tell us what K is, right? What's K? Well, we got chart 14 for that. So let me see if I got chart 14. I think I put most of these on Blackboard, the ones that we're using tonight. Branch entry, yeah, we got it. Okay, here we go. First of all, why did they cross out 60, 75, and 90? Any idea? I didn't do that. Crossed out in the textbook on the table. They crossed it out because you're a maniac if you try and use those angles. The losses are enormous. I mean, it's not really appropriate. In other words, here's a message. Don't use these angles, right? So for us, 30 is pretty severe even, right? So 0.18 is what K is equal to, okay? So K is equal to 0.18. Okay, I'm tempted to say it's unitless, but I think the units may tie in somehow or other so that we wind up with the right units. So what's the velocity pressure equal to? The velocity pressure is equal to, again, it's equal to, do I have all the information I need here? I got the velocity. Yeah, I got what I need here, right? Where am I? Yeah, 1.3? Okay, 1.3. Okay. And the static pressure loss, what's that going to be equal? You're going to be equal to K times 1.3. Okay, that's equal to 0.18 times, whoops, didn't mean to do that, but that works good, times 1.3. Okay, which is equal to, what does that come out to be? 0.2 was that? 0.3? Okay, 0.3 inches of water. What's that? I'll take your word for it. It's just a little bit of math. So what does that mean? That means in order for this, whatever the static pressure is here, where we're going into this transition, right? Whatever the static pressure is here, the static pressure on the other side of it has to be 0.3 inches more negative in order for this to work. Make sense? because the static pressure here has to be lower than the static pressure here for the air to move in that direction, right? And if you didn't lose a lot of energy, if this branch were 15 degrees instead of 30, then this would be zero point 0.1 times 1.3 to be a tenth of an inch of water, let's say, right? So this would have to be just a little bit more negative than here in order for this to work. Just keep in mind static pressure as you move through the exhaust system towards the fan, the static pressure gets more and more negative. And what determines how negative it has to be is, is how much frictional losses you have between the fan and the hood.